We are finishing up the entire part 2 of our course today. This is the last lecture on support vector machine, and that's also the last lecture on part 2. I hope by now we have enough tools in your pocket that you will at least be able to say, if I want to do a classification problem, I have method A, B, C, D, E to apply, and they're not that different at all. Okay, they're all linear models. If I need to embrace nonlinearity, I have two things I can do. One is kernel trick. The other one would be deep neural network, just have multiple layers of networks stacked together. Before we move on to part 3, I want to spend one more lecture on support vector machine, just to discuss two additional concepts about support vector machines. One is the notion of soft margin. That will allow you to create a decision boundary where your data set is not linearly separable. That is usually the case that you need to deal with. The other topic that I want to go over is how do we do kernel-based support vector machine. In other words, how can we put these kernel tricks into the support vector machine problem so that we can have nonlinear responses. All right. Now, there are two parts, as I have told you. Part 1 will be on soft support vector machine, and part 2 will be on kernel trick. Specifically to the soft support vector machine, we want to go over the formulation and talk about the optimization problem. No more algorithm, because by now we should feel comfortable by saying that, look, this is a convex problem, and then I'm going to apply a convex solver to solve the problem. And then I will move on to talk about kernel tricks and discuss how this dual form that we discussed last time can be used to solve the dual SVM problem. So to start with, let's talk about linearly separable. Suppose you have a data set that looks like this. You have all the blue circles, and then you have all the red triangles. Now, if I ask you to run a classification algorithm, okay, now you have multiple choices now. Okay, you can have a Bayesian decision rule, you have logistic regression, you have perceptron algorithm, you have support vector machines. So suppose I ask you to run a perceptron algorithm. Guess what will the perceptron algorithm do? The perceptron algorithm will say that I want to look at this data set and I want to make sure that all the data points has been correctly classified. I don't care about the margin. I just care about the accuracy. And this is going to be returned by your perceptron algorithm. Now, we understand the perceptron algorithm is non-unique, and so you have multiple solutions. This is just one of those. Okay, and we agree that this is an allowed solution because it has already correctly classified the data set into two halves. Now, you move on and you say, can I run a support vector machine, the hard case, using the things that we have learned over the past 2 lectures? Will we be able to get a better decision boundary? And this is what will be returned by your support vector machine. Again, you get a decision boundary that is very close to the data points. However, it is still a legitimate decision returned by support vector machine because all the constraints are satisfied, and then you are finding me the biggest margin. And imagine that this is really the biggest margin that you can find in this case. Okay, and you look at the data set and you say, I'm not too happy. Why? Because if I run the logistic regression, by logistic regression, I can tolerate some samples to be misclassified. If I run the logistic regression, I probably will not make this decision. And if I run a Bayesian decision rule, I will just treat it as an outlier, and that will have negligible contribution to my mean and my covariance matrix. So it may not affect me too much. And if that's the case, I will not get this decision boundary. What do I get? Well, we will expect to get something like this. Okay? So we ask, now support vector machine is such a powerful thing, right? Because you can design the margin, it's max margin classifier. why can't we just impose some additional capability to the support vector machine so that instead of returning this classification decision, I want to have a classification decision like this. What am I paying? What is the price that I'm paying? I'm paying the price of having one sample that is misclassified. And is it a bad thing? Well, I can just read it as a outlier. And so if this is really an outlier and misclassifying that, may not be that a big issue to me in terms of the testing error. Okay, and what is the good about this diagram here? The good about this decision boundary is that the margin is a lot bigger than the previous case. So you're paying the price of one misclassified sample points, but then you're gaining the margin for all the other sample points. So that would be something that we want. Okay, so how do we achieve this goal? And that goes to the discussion of soft support vector machine. And to introduce this soft support vector machine, I need to introduce the idea of soft margin. Now, we go back to the original hard margin case, where we call that the constraint is given by this equation, where you have a label y, and then you have a discriminant function w transpose x plus w0. And then it has to be bigger than 1, that is in the normalized space. It has to be bigger than 1 for all the samples so that you have a margin. Now, if this is the margin, can I do a small change to this formulation by subtracting the right-hand side with a number, psi j, with the condition that all the psi j's, they are positive. So what is happening in the diagram is this. You have a decision boundary. What is the original decision boundary? Well, the original decision boundary says that it will be this, right? So this is the case of 1. Okay? So now I am going to allow you to have okay, so if you really set 1, then that would be the margin. Okay, so now if I allow you to have this minus a psi j here, what I will allow you to do is that I will allow you to have sample data points that can go across the decision boundary. Okay, or if I want to view it in this way, if this is the margin, okay, if this is the margin, I will be able to have sample points that is living inside the margin. Okay, so now what is the difference between this one? In this case, you have your decision boundary here, you have your margin here. There is no points that would be allowed to stay inside. With this constraint here, if this is the same decision boundary and then you draw the margin, you will allow to have data points that is living inside this space. Okay? So essentially what you're doing is that I am going to make this margin a little bit bigger, okay, so that I can allow training samples to live inside the margin. And in order to do that, I need to introduce another variable by making this margin smaller. Okay, so if I do this, then you can see that the problem would become the following. Instead of just minimizing this 2 norm square of the w, I will have a constraint with 1 minus psi, and then I have psi j bigger than 0. So I'm changing my hard constraint support vector machine to a soft case. And by soft case, I really mean that I have additional criteria on the side. Now, let's look at here. In the optimization problem, I'm not just minimizing the w. I also want to minimize with respect to the psi. Why? Well, because if I fix a psi, then I'm not allowing myself to move my decision boundary. Okay, so because if I fix the psi and fix the margin here, then I'm restricting myself to this particular margin. Okay, I don't allow me to move left and right, up and down, because by moving left and right, up and down, the margin may not be the same as the psi. And so I also want to make sure that I want to find a good psi such that all these are satisfied, and in addition, this is minimized. So this psi will now become part of the optimization problem. Is this a much harder optimization problem? It's not a much harder optimization problem because this is just one more additional variable in the linear form. And so this entire problem remains a quadratic minimization. So it's still convex. You can still use the CVX to solve the problem. So everything will still come out. However, the benefit that you're gaining is that now you can allow a few data points to be misclassified. As for how many data points will be misclassified, you don't know until you solve the problem, because the number of data points that will be misclassified, it really depends on the psi. And now, since psi is a variable, you can look at this problem. This problem will say that the psi cannot be arbitrarily chosen. In particular, if you do not put any constraint on this psi, what will happen is that since I want to minimize this thing, subject to all these constraints, as long as my psi j is plus infinity, okay, as long as my psi j is plus infinity, then the left-hand side will always be bigger than the right-hand side. No matter what w you choose, no matter what xj's you have. Okay, so if psi j is plus infinity, then this right-hand side will become minus infinity. So here it will become minus infinity if this psi j is plus infinity. If this happens, then whatever you have on the left-hand side will be satisfied. And so you can choose whatever w you want. And so that's not going to solve the problem. Okay? And so what you will need to do is to also constrain the magnitude of the psi by putting a regularization function here. So instead of just minimizing with respect to the w, you also say, I want to have a regularization that the 2 norm square of my psi is part of the optimization problem. And by doing this, I will not allow situations like this to happen. Okay, I want to make sure that my psi is as small as possible. So what does it mean? That means I want to stick to the hard margin as much as I can. All right? However, I do allow you to have some kind of soft decisions. Now, as for how much soft decisions you can allow, that is controlled by this parameter c. If you make the c extremely big, then that means you don't really allow any big psi to appear. Okay, so if it's c big, then this 2 norm square of psi has to be small. Because you're solving this minimization problem, and if c is big, then this term cannot be big. Okay, so if this is small, then that means you are getting closer and closer to 1, right? Because if psi j is very small, then the margin becomes a hard margin. So you're not doing much better. But on the other hand, if you make the c extremely small, then you can let the psi to grow. Then what you are allowing is that you are allowing a lot of samples to be misclassified, and you're saying that I'm able to tolerate more. So the impact of the c can be visualized in this set of diagrams. If c is big, then you are making the psi to be small, so you go back to the hard margin case. But as the c becomes smaller and smaller, so you go on this axis, when you make it smaller and smaller, then you can see that you can have more and more data points being misclassified. So for example, here, this is the hard margin case. If you have a very, very big c, the decision boundary will be pretty much the same as this one. As you reduce the c, then you can see that the number of data points that can go inside the margin will become more and more. Okay? And as you go all the way to a very, very small c, then you will have a lot of samples that will live on inside the margin, and that will be your decision boundary. Okay, so this is the role of the c. And we can also ask, what will happen to the misclassifications, and how do you measure this psi? So this diagram shows you the meaning of the psi. The psi is measuring from your margin to a data point. Okay, so let me draw it more clearly. So this is your margin. Okay, and then this psi, this is the psi, is measuring from the margin to the data point. And here it will be measuring from the margin to the data point. So for every data point, you can have a psi. Okay. Now, so now when you have this problem, when you have c equals to 1, then you have extremely small c here. So you let this psi to grow, and therefore this margin can become big. In this case, the margin becomes small. And because you're changing the psi, this decision boundary will also change, because psi is an optimization variable. If you make the c bigger or smaller, this optimization variable will change. So you ask, can we replace my 2-norm square by something else? And of course, yes, you can replace the 2-norm square by whatever regularization you want. You can put a 1 norm, you can put a 1.5 norm, you can put whatever norm that you want. In this case, I'm just putting a 1 norm here, and then you can also get a solved margin. Okay, it's just not as easily solvable as the other, but that's still a convex problem, so you can still dump it into the convex solver and get a solution. I want to draw some connection between the support vector machine and also the perceptron algorithm that we have learned so far. And in fact, if you remember, how do we go to the support vector machine? We go to the support machine by saying that the perceptron algorithm doesn't have a very good margin, and therefore we want to use support vector machine to find a max margin classifier. And because of this motivation, we should think that there should be some connection from the support vector machine to the perceptron algorithm. And here is the connection. So let's look at the soft margin support vector machine case. And you have a pair of constraints like this. So if you write them out and rearrange the terms, then this constraint can be written as the psi j is bigger than 1 minus all your discriminant function on the right-hand side. Okay, so now what you can do is that you have a pair of conditions, and they are related by and. Okay, so you want this to hold. Okay, so you want psi to be bigger than 0 and psi bigger than this one. So when will this happen? Well, this will happen if psi is bigger than the maximum of the two. If psi is bigger than the maximum of these two, certainly you will satisfy criteria 1 and criteria 2. Now, what is this? This should look a little bit familiar, right? Because if you recall the perceptron algorithm, you have something similar to this. It's just that you don't have the 1. Okay, I'm going to discuss this point in the next slide. Okay, so but this point is that when you look at the constraint that you have in the perceptron algorithm, it looks in the support vector machine, the solved case, it looks very, very similar to the perceptron algorithm. Now, I can also simplify this notation by using this symbol. I can just say that I put a bracket and then with a plus. That is just trying to say that you give me any number, I'm going to give you the positive side of that number. Okay, because if this quantity is bigger than 0, I'm going to return you this quantity. If this quantity is less than 0, I'm going to return you 0. And this symbol with a plus here really says that it will just become whatever that you have here, or 0, if that thing is bigger than 0, if that thing is less than or equals to 0. Right? So this is a shorthand notation of this max operation. So now if I use this shorthand notation and put it into the L1 penalty, so L1 penalty means this regularization, instead of using a 2-norm square, put a 1 norm here, then you can observe that this objective function would become half of the W2 norm squared plus C times the summation of the size. Why? Well, because the psi of one norm is just the summation of the absolute value of psi j. Okay, and what is psi j? Well, psi j by all the construction, psi j is they're positive, and so this is the same as the summation of the psi j because the psi j is positive. And so I can write my one norm case. I want to highlight that this is one norm penalty. You can write it as this objective function. And now what is psi j? Well, the psi j, I can put it in, can just put this number here. Okay, I can just put this number here because, right, okay, so I can put this number becomes greater than or equals to, right? Because if I put the psi j here, this is my definition, I can put it here, then this is really my max operation, right? Because psi j is bigger than this. And so if I can minimize this, then I will be able to minimize this lower bound. So what? Well, so that means the training loss will become this. You have this objective function where you have the 2 norm square, and then you have all these constraints here. Then this C can be somehow absorbed to this lambda square over 2 of 2 norm square W. Because I'm just letting lambda equals to 1 over C. So if I make that assumption, then my objective function becomes this. And now, if I can make this lambda go into 0, that means your C has to go to plus infinity. Then what will happen? Well, then you can ignore this term. You ignore this term. Then your objective function will become this. Okay, just this term. And since you have the max operation here, then you can look at this. This is just 0 and 1 minus of this y. This is exactly your discriminant function, right? So this is your discriminant. They are the same, and so your objective function would become this. Okay, so what will happen next is that the support vector machine loss actually has a very similar form compared to the perceptual loss. Is there any question? Okay, if you have questions, just let me know, all right? Okay, so this is the support vector machine loss where you have this 1 minus operation in front of the discriminant function. And then here is the perceptual loss, and you can see that the difference between these two is the presence of this 1. So what is the conclusion here? Well, the conclusion here is that the support vector machine, the soft case, okay, so the soft case, if you use the 1 norm penalty, and if you send the parameter lambda going to 0, then the support vector machine loss will become the perceptual loss. Okay, so these two are not that different at all in the limit case of the support vector machine. Then you ask, then what is the benefit of support vector machine? Well, if you remove all these limiting cases, then the support vector machine actually buys you the margin, buys you the soft decision, buys you the robustness, where the perceptual algorithm is not going to be able to offer you. And that's why the support vector machine is a lot more powerful than a perceptual loss. So we call this diagram, this is all the loss functions that we have so far, right? So we have the perceptual loss is one of those. Perceptual loss is the green one. And then now the support vector machine loss, if you go to the limiting case, it will be one of these. Now you have this max of 0 and 1 minus the thing. That will be this curve. Okay, I think it will be this curve. It's because this is the perceptual loss. And now when you have a 1 minus this, then you are moving it to the right. All right. So that is the discussion about soft support vector machine. I think we are convinced that the soft vector machine is able to help us get some margin, and that should allow us to generalize a little bit better in the case where the two classes of data points, they are not linearly separable. Okay, so now you have overlaps, you can still run the soft SVM to get a solution. In fact, if you have a real data set, you are highly encouraged to try the soft SVM first, because that will allow you to have some tolerance of your data set, which you never know how they're going to overlap or not. And in the soft SVM setting, there's always this tunable parameter C. Okay, and this tunable parameter C is something that you want to make it bigger or smaller by trial and error. And after all these trial and error, you'll be able to find out a C that will work well with your data set. Okay. If you start with a hard SVM, and if your data set is overlapping, then you just will not be able to get any solution. So the soft SVM will buy you a lot more flexibilities.